bitter end. This will be the last lecture per se, and then on Friday we'll do the course review and the course evaluation as promised. And what I said I was going to talk about today were nuclear weapons. So we've been talking recently about applications of nuclear science. They've been mainly beneficial ones. This is certainly not a beneficial one, but it's a reality, and so it's important to talk about it and try to understand how the nuclear physics we've been discussing this semester plays a role in making these terrible things work. Okay, and just a reminder of the final. Okay, and let me get this going as a slideshow. Okay, fine. Okay, so nuclear weapons. Remember when we were talking about the basic ideas of what makes a nuclear reactor work, what were the conditions required? We were going to make use of fission of uranium to produce energy and also produce more neutrons to allow a self-sustaining reaction to happen. And the quantity that we talked about that was of interest here was something called K, the neutron multiplication factor, which is a measure of how many neutrons there are in each succeeding generation of fission events. And so the cartoon over here on the left sort of illustrates this. You have one neutron initially, and let's say it encounters a U-235 and causes it to fission. It produces energy in that process. These two blobs are the fission fragments, and in this particular reaction, 3 extra neutrons were created. And so in that second generation, so in this diagram, the first generation is that first neutron hitting the first U-235. The second generation now has 3 neutrons in it. And in this cartoon, 2 of them hit uranium nuclei. One of them hits a U-235 and causes another fission to happen. One encounters a U-238. And as you know, at least if these are low energy neutrons, which most of these are, chances are you won't get a fission event from U-238. You'll get a capture. And so here, one of those 3 neutrons in the second generation succeeded in making another fission, and you get this multiplication factor. Okay? And if you want to run a reactor in a very safe and steady way, you want the number of neutrons to remain constant. You don't want it to go up. You don't want it to go down. If K is less than 1, then you'll have an exponential decrease in time with the number of neutrons. And the time scale, as we saw, is very short, because what matters is the mean time between generations. And when we were talking about a reactor, we were talking about thermal neutrons, really, because we had lots of moderator around. In terms of a bomb, we want things to happen very, very fast. We don't want a slow rise in the number of neutrons. We want to get as much bang for our buck as we can, as fast as we can. So there are no moderators in this. And what that means is you're using fast neutrons to do the fission. So that's a difference between what we were doing in the reactors, where we wanted to maximize the fission cross-section, which meant slowing things down, getting them to thermal energies where the cross-sections were hundreds of barns. Here, as we're going to see in a minute, if you try to do it slowly, you won't get a bomb. You'll get some nasty event, but it won't make very much energy. It won't do the damage that these things are designed to do. So to get the big blast, you have to do it very, very fast. So the fast neutrons are what's inducing fission in a bomb as opposed to a reactor. And then you can ask yourself, what is the time scale between generations here? And we'll see in a minute how to do the calculation, but it's very, very short. And so you get an exponential increase in the number of neutrons in a very, very short period of time, leading to more and more fissions as time goes on. And you end up fissioning a fairly large fraction of the total mass of uranium-235 that you had. And here's another sort of cartoon showing the multiplication, indicating that you get more and more neutrons and more fissions as you go from one generation to another. And what got cut off at the bottom of the slide here is an important disclaimer before I go any further, that all this material that I'm telling you today is totally unclassified. It's totally publicly available. You can find it on the web. I'm not giving away any secrets here, okay? I don't know any secrets, and I wouldn't give them away if I did. And if you're interested, in more details than I'm going to tell you, there's a remarkable book. It's called the Los Alamos Primer. It was written in the 1940s during the Manhattan Project. It was actually a series of lectures that a young graduate student gave to the new recruits who were coming in to work on the design and building of the bomb. The Department of Energy wishes they had that they had classified it back then, but they didn't. So it's publicly available. And what's remarkable is, first of all, there was a graduate student who was doing this. He was the one who gave the lectures, a guy named Bob Serber. And in 1942, when these lectures were given, they already knew everything about how to make the bomb. I mean, you read this book, and it's remarkable because you'll go through the first few pages, and after Nuclear Engineering 101, you'll be nodding your head saying, yep, I understand all that, the basics of nuclear radioactive decay and barrier penetration and nuclear fission. And then right away, chapter 2, they start talking about neutron transport. And you have to remind yourself, they had no computers back then. You know, they had slide rules and pieces of paper and pencils. They worked it all out, and they knew exactly how to do it. So very, very good people, very interesting stuff, if you're interested. The Los Alamos Primer. Okay, so in order to make this happen, in order to get this chain reaction to happen and to proceed in a very fast way, we need to produce a certain amount of material so that this multiplication will occur. If I have a little tiny bit of uranium and I produce a fission, chances are those neutrons that are produced will not encounter any more uranium, and that'll be the end of the story. What I want is to have a big mass of uranium or plutonium sitting there, so that when I get a first fission happening, there's a really good chance that the neutrons produced will run into another uranium and make another fission happen, and so on and so on. And the quantity of interest that you can calculate to figure out how much uranium you need to make this happen is what's called a critical mass. And it's the amount of material you need to assemble to make that K factor, the multiplication factor, greater than 1, so you get this exponential runaway. So let's see how big it is. And this, again, is a crude estimate. It's not meant to be very quantitative, but it gives you the order of magnitude. And so if you want to have a neutron that was produced by a given fission produce another fission, what that means is you want an amount of material such that the neutron travels on average no more than one mean free path in that material before it escapes. So let's calculate the mean free path of a 2 MeV neutron, which is the typical kind of neutron energy you get in fission. So the mean free path is related to the density of the material and also the cross-section for the reaction we're interested in. If you go back in those tables in Lily's book when we were talking about fission, you can look up the absorption cross-section for 2 MeV neutrons on U-235, almost all of which leads to fission. It's about 2 barns. And the other factor I need then is the number density of uranium atoms that will be in a uranium sample. So I need the density of uranium, I look that up, divided by the atomic weight of uranium multiplied by Avogadro's number. It turns out the density of uranium under normal conditions is about 16 grams per cubic centimeter. So the number density of uranium atoms is about 5 times 10 to the 22 per cubic centimeter. And so I can then calculate the mean free path using the formula up there. It's on the order of 10 centimeters. That means that on average, a neutron will travel about 10 centimeters before it encounters another uranium. So if I had a U-235 sphere with a radius of about 10 centimeters, I would have a critical mass. I would have enough material so that there's a very high probability that that neutron that came from the first generation will hit another uranium nucleus and then cause another fission. And if I have a sphere that's 10 centimeters in radius, you can calculate the mass, 4/3 pi r cubed rho. It's about 60 kilograms. Okay, so to use 5 as a nuclear fission weapon, you need a mass on the order of 60 kilograms. Okay? And notice that I'm assuming here I've got pure U-235. I'm assuming that all the uranium atoms are really U-235. So to make this work, you have to enrich the uranium. And this is a plot showing the critical mass that you need as a function of the enrichment. So below a certain point, you actually can't get enough. Okay, you can't really make a bomb out of natural uranium no matter how much you have because there are too many neutron losses. But once you get above, say, 20% or so, you can see the curve comes down rather steeply. And out at 100, the number's something like the calculation I just did. I mean, it's actually a little bit less, but not so far off. So a lot of effort went into developing techniques to enrich uranium back during the war, specifically for this purpose. And I'll show you some of those facilities in a minute. U-235 is not the only material you can use, of course. There are other fissionable nuclei, and this is a similar kind of plot for other fissionable materials that could be used to make a bomb. So here's our U-235. This is a little bit more refined estimate than the one I just gave, but you can see the order of magnitude is right. Notice plutonium. It takes a lot less plutonium to make a nuclear weapon than it does uranium. For reasons you can probably figure out. One is that it has a bigger fission cross-section. 2, the density is higher, so on. And notice U-233, Neptunium-237, Americium-241, all in principle can be used to be the fuel for a nuclear weapon. I don't think all of them have actually been used, but most of them have. during the Manhattan Project, there were lots of experiments that were done, and there was one famous one. Oh, darn, this got cut off too. I think it was called something like teasing the tail of the tiger. And what these guys were doing were trying to very carefully assemble a critical mass of plutonium and measure the neutron field and the gamma field that got produced as a result. And unfortunately, things went very bad. There's a movie where this was recreated. One person died a very horrible radiation death in a few days, and I think another person died sometime later. This is a reproduction of it. This is the plutonium sphere. It was in two pieces, and they were trying to bring it together and watch the radiation that was being produced as the fissions began to happen. This was a neutron reflector made out of tungsten, and unfortunately, something got dropped or something went a little faster than was supposed to happen, and there was a blue flash, which meant the thing went supercritical. There wasn't an explosion. The heat that was generated actually pushed the sample back apart and turned it off, but the radiation dose was lethal for the folks who were around it. The point is that it doesn't take very much. I mean, that's something like that 10-centimeter ball I was talking about. So something the size of your fist is serious. Pardon?
That looks way bigger than that.
No, it's not. This is a close-up. It's something like that. So to make the U-235, various enrichment techniques were used, and the original idea was to use electromagnetic separation, and that was developed actually at Lawrence Berkeley Lab. The 184-inch cyclotron at LBL was used initially to demonstrate the technique, and then it was realized that it couldn't be done on a large enough scale to make kilograms of material, which is what you need. And so a facility at the Oak Ridge National Laboratory was built. These devices are called calutrons. The CAL is for us here, okay, because it used the idea developed here. These are big electromagnetic separators. They would take natural uranium, ionize it, run it through a magnetic field, and the radius of curvature, as you know, depends on the ratio of the charge to mass. And so U-235, because it's a little bit lighter, would get bent more in the magnetic field than the U-238. And what they had at the end were big chunks of graphite. These were receivers, they called them. And they would have a little pocket over here and a little pocket over here, and the 235 would end up here and the 238 would end up here. And they would run these things for days and days and days, and then pull these graphite receivers out and actually scrape the stuff out, okay, knowing that the 235 would be over here, the 238 would be over there. And gradually they built up many, many kilograms of uranium that way. So you probably all have seen this before, but there are two basic ways to make this work. We know how much material we have to get together. We want to produce that right at the instant we want the explosion to happen. We don't want to have a critical mass of uranium sitting around where we're going to get exposed to enormous amounts of radiation, or the thing would slowly fission, not rapidly. So the idea is to start with one or two or more pieces of uranium, or plutonium, let's say, each of which is less than a critical mass. We bring these two together very, very rapidly to form something at least as big or more than the critical mass, and then we trigger the explosion. And there are two basic ways to do it that were realized back in the Manhattan Project. One is called the implosion technique. And the idea here is you start with roughly a critical mass or a little bit more of the material, but in separate pieces, or at least in a hollow arrangement so you don't actually have a good geometry for the explosion. And then you have a set of chemical explosives arranged around it that you ignite and produce a very symmetric explosion, so you actually compress the material which was in here. Okay? So you have chemical explosives around the outside, you have the fissionable material inside, you set off the chemical explosion. Because it's a very symmetric arrangement, you actually get an implosion of the material that was inside it. And the trick to doing all this is to get this explosion to be extremely uniform. So you have to time the explosions just right, so all these little explosions are going off at the same time, and that the energy is being directed to the center, so you actually get a compression, and you actually form the critical mass very quickly. This was something that was considered to be very difficult back in the 40s, and so it was felt that one needed to do an experiment to test whether this could actually work before we used it as a weapon in the war. And so the first test of nuclear weapons that was done in Alamogordo, New Mexico, was of this type, the implosion type, because they weren't sure it would work. The other type they knew would work. They didn't even test it before it was used as a weapon. And that's the gun assembly, as it's called. And the idea here is you just have two pieces of uranium which are separated initially so that each one is less than a critical mass. And you basically shoot something at it and compress it, force these two pieces together, and make a critical mass very quickly. So basically a cannon type assembly, and I'll show you some pictures in a minute. And this was the one that was done. This is the one, I'll tell you in a minute which bomb it was, I've forgotten. But this one was used without ever testing it initially. Now, you know, what I said originally was you just bring a critical mass together and you get an explosion, but that isn't exactly right. Because remember in that diagram I had, you need a neutron to start that first fission happening. And we don't have any neutrons around here. So what also was realized way back when is you need to have a trigger of neutrons just at the right time. So just when you form the critical mass, either in the implosion type or the gun type, you need to have a source of neutrons there. And again, you don't want the neutrons to be there beforehand, or you'll start the fission happening as the thing is being attempted to assemble, and you'll actually fizzle. It won't go off as a bomb. So what people in 1942 realized, they needed to make neutrons. They had very primitive accelerators in those days, so they didn't think they could use that in a weapon, but they had radioactive sources around. And we've talked about this before, too. So the way they generated the neutrons that they needed just at the right instant was they had a source, and most of the sources were polonium-210. This is a nice alpha emitter. It emits alphas of about 5.3 MeV. And what they did is they had beryllium-9, and what you get is helium-4, the alpha particle, plus beryllium-9, making carbon-12 plus a neutron. And in order to make this happen just at the right time, they would essentially have a foil, let's say, of polonium-210, and another foil of beryllium-9. And you know the range of alpha particles is very short, so as long as you have the two foils, or whatever the physical form of these things is, it doesn't matter, as long as they're physically separated and you have maybe an inch of air or some material in between, you won't have any nuclear reactions happen. So you can use the explosion to bring these two things in contact with one another. And as soon as they're in contact, now the alphas can initiate the reaction. You produce the neutrons just when you want them to be there. Yeah?
If the mass is sitting at near criticality there,
yeah,
and the weapons are sitting around for decades, you worry about the
So you tell me. I didn't put this on here, but since we're talking about U-235, the half-life is 700 million years. We're not going to worry about it. Plutonium-239 is 24,000 years. We're not going to worry about it. However, there are other effects that happen from these things sitting around, which people do worry about, which has to do with the metallurgy of the material. Very often, what's in the bombs is metallic uranium and or plutonium with other things added in for various reasons. The question is, what happens to that metal as a function of time because of all the alpha decays which are happening in it? First of all, you get dislocations in the material from the alphas and the daughters recoiling. Second of all, the alphas stop inside the material, and what you generate is helium gas. And so there have been a lot of studies over the years as to what happens to this material as it so-called ages. The conclusions I've read, which again are not classified, is that basically nothing happens. Okay, that's not going to be a problem. There are other problems, though, which we'll get to in a minute when we talk about fusion weapons, which has to do with the fact that you need tritium for those. And tritium has a much shorter half-life. It's 12 years. And so there we actually do worry about the fact that the tritium is decaying away and you need to replenish it every once in a while. But here, we don't worry about the radioactive decay depleting the fissionable material. We do worry about mechanical issues. That's a different story. Okay, so we make the neutrons just when we want them. And then here are the bombs that were actually used. This was called Little Boy. This was the Hiroshima weapon. So this was the first nuclear weapon used in war. This was the gun type assembly, which, as I said, was never tested because they were so darn sure it would work. And it used U-235 as the fuel. The second nuclear weapon that was used during World War II was what was called Fat Man. This was used on the city of Nagasaki. And this was an implosion type bomb which used plutonium-239 as the fissionable material. It turns out that you can get very, very pure U-235 through the enrichment process. How do you make plutonium-239? How do you get it? We actually talked about this too. You don't dig it out of the ground. Exactly. So you throw neutrons at U-238, so you have to make the plutonium-239. That's the important thing. And you need a nuclear reactor to do that, to have enough neutrons. So you do 238 uranium plus a neutron to make 239 uranium, which then beta decays to neptunium-239, which beta decays to plutonium-239. Okay? And this half-life is something like, I forgot, 20 minutes. And this one is something like 2 days. And this is 24,000 years. So this builds up in the reactor. And in fact, there was another major site, the one in Hanford, Washington, that was built during the Manhattan Project to produce the plutonium for nuclear weapons. And it used exactly this process. One issue with this whole thing, though, is that while you're making the plutonium, you go through this chain. The chain doesn't stop there. So the plutonium itself can capture neutrons. And it'll make plutonium-240. It can also undergo fission. So when you pull the fuel out of the reactor and you chemically extract the plutonium you've made, you actually have a mixture of different isotopes. And this isotope, it turns out, has a reasonably large spontaneous fission branch. So it produces neutrons before you actually want them. And so there are special ways the weapons-grade plutonium is made, but nevertheless, you can't use a gun-type assembly to make a plutonium weapon go off. It'll fizzle. It'll fizzle with the Z, not with the S's, meaning it won't go off as a bomb because of the neutrons that are already there before you want them. That's sort of a tongue twister. So the implosion-type weapon is what was used for the plutonium bomb. And here are some more cartoons of it. This is a cartoon of the Fat Man design. So rather than just two equal sort of pieces, the way it was done is you actually have a hollow bullet. You have an explosion go off in the barrel of the gun. It accelerates this thing into another target. And when they come together, you form the critical mass, and you trigger your neutrons. As I said, when these were first done, they were radioactive sources that were used to generate the neutrons. Nowadays, it's actually a little accelerator. They're called zippers that are used. They're in the weapons to produce the neutrons. And it's a DT kind of reaction, like the fusion stuff we talked about a couple weeks ago. So you make 14 MeV neutrons just when you want them. And if you don't bring it together fast enough, so here are two pieces we're trying to bring together, you bring them together rather slowly. What happens is you get a little bit of fission happening, so you get some energy generating, you get some pressure built up, and basically you spread the two pieces apart again. You make a mess, but you don't make an explosion. And in a weapon, that's not what we want. Okay, so this is a picture you've probably all seen. This is a photograph of the very first test that was done. It was called the Trinity test. So this was one of these implosion-type weapons that they did, and that was the blast. There were various ways people estimated the yield of this thing, that is how much energy was generated. And the story was told about Enrico Fermi, who was one of the physicists who worked on this. He was standing like a mile or two away, and the story is he took some paper and ripped it up and dropped it just at the moment of the blast. And by measuring the shock wave and how much it displaced the paper, he calculated the yield. And of course, because it was Fermi, he supposedly got it right to within 10 or 20%. Unfortunately, this is what then happened. So very soon after that, I apologize, my legends have gotten cut off here. This is the Hiroshima blast. So this was the first one that was dropped on the city of Hiroshima. And what it says down here that you can't see is that, very tragically, 140,000 people were killed as a result of that blast. So this is bad stuff. I mean, this is really horrible stuff. This is some of the aftermath. This is what the city looked like after the bomb went off. I mean, there ain't much left. These are not like conventional explosives. These are very, very different. Okay, they're much worse. Because, yeah. This was done in the air. It was deliberately done in the air, yeah. So they dropped it from a plane, had a timer on it so it would explode while it was in the air, right? Yeah. So, of course, there's the initial explosion, incredibly high temperatures, things are vaporized. You know now about the radiation that's produced, lethal doses of radiation over very wide areas. Yeah, these are really horrible things. This is a map of where the damage was over the city. This area in red is where the fires were that happened as a result of the bomb going off. What's remarkable, I have to say, is Hiroshima is a thriving city today. I mean, it has recovered from this. Again, not to minimize things, it's remarkable that it is possible to recover. And then this is Nagasaki. This was the plutonium implosion, and this event killed 80,000 people. Over the years, we, the Soviet Union, China, a number of other countries developed all kinds of nuclear weapons, and some of them are pretty amazing. These were nuclear weapons that got shot out of a cannon. So a nuclear weapon would be shot out here, and that's the explosion. People were crazy. And we and the Russians did thousands of nuclear tests, and I'll show you the numbers in a minute. There's a place called the Nevada Test Site out in Nevada, where we set off several thousand nuclear weapons. I mean, it's absolutely amazing. And did all kinds of experiments to figure out the optimum designs to make as big an explosion as you want, or to maximize the amount of radiation that it produced. Whatever you can imagine, they did. And there were thousands and thousands of scientists and engineers involved in building these devices, doing the tests, analyzing the data. And remarkably, there's still people analyzing the data from those experiments. Because, as you can imagine, you make a lot of debris in these things. And there were trained physicists, engineers, chemists who would go out and recover some of the debris and then analyze it in terms of both stable and radioactive isotopes that got produced to learn about what actually happened in the explosion. Because one thing I forgot to mention, which we should go back to, I started talking about the time scale for this. Go back for a minute. So what we're thinking about in these weapons is we've got an object about 10 centimeters in size, and we've got 2 MeV neutrons. So let's think about how long it takes a 2 MeV neutron to travel through something that's 10 centimeters in size, because that's the time scale between the successive generations in the weapon. Okay, so 2 MeV, non-relativistic mechanics works. So a half mv squared, I'm going to say is 2 MeV. I did this in my head on the way down from my parking space, so let's see if I can reproduce it here. I think I got the right answer. Okay. I mean, it tells you the kind of things I think about when I'm walking. Right? Obviously a nerd, right? Okay. Okay, so I want to get the velocity to figure out the time it takes it to travel 10 centimeters. Okay. So I'm going to say, I'll multiply both sides by 2. So I've got mv squared is 4 MeV. And then I'm going to say that the mass of a neutron is about a GeV. And therefore, it's actually mc squared. So I'll put a c squared here, and I'll put a v squared over c squared there. So v squared over c squared is going to be 4 MeV divided by 1,000 MeV. I'm rounding off, of course. So this is 4 times 10 to the minus 3 is v squared over c squared. Okay? So I can't do square roots like that in my head, so I'm going to change this. I'm going to say that's 40 times 10 to the minus 4. Okay? And then I say the square root of 40 is about 6. So v over c is about 6 times 10 to the minus 2. Okay? And we want to go 10 centimeters, right? So c, which I would give you on an exam sheet, of course, is something like 3 times 10 to the 10th centimeters per second. So I multiply v over c times c, and I'm going to get, rounding off again, 20 times 10 to the 8th centimeters per second. Yes? This is my v. 2 times 10 to the 9th centimeters per second. And I want to go 10 centimeters. So it's going to take me a few nanoseconds to do that, right? Several nanoseconds. So the time scale between successive generations is several nanoseconds. And historically, the unit of time that was used was 10 nanoseconds. as a measure of the time between generations. And historically, that unit of 10 nanoseconds was called a shake. So each generation is one shake apart. And it takes 50 or so generations to make the bomb go off. So if you think about it, the whole explosion happens in less than a microsecond. The actual explosion, the fission process, takes less than a microsecond to happen. Okay. And then, of course, in addition to measuring the yields and debris and all that kind of stuff, they wanted to see what effects this stuff had on various objects. So they would build houses and towns, actually, and then set the bombs off and watch what happened. Okay? And these aren't very clear pictures, but these are buildings being demolished by the nuclear weapon. Yeah?
How did the two, original atomic bombs?
I think in terms of the number of tons of TNT equivalent, I think they were similar. They were on the order of 20,000 tons of TNT each. People went back and tried to figure out what fraction of the fissionable material actually fissioned. And I've forgotten the numbers, but one of them was much better than the other in terms of succeeding in fissioning more material. One of them was just like 5%. I think the other was 10 or 20%. I don't remember which. You can look it up. Unfortunately, by today's standards, these were small weapons. Okay, 20,000 tons of TNT sounds like an enormous amount, but there were weapons built later that we'll talk about that were millions of tons of TNT equivalent, many millions of tons. So, a big nuclear weapon going off, let's say in the middle of the bay, would wipe out a fairly large fraction of the entire San Francisco Bay Area. So even though these fission weapons were horrible, people thought we needed even bigger ones. And there were crazy people in this country and in the Soviet Union who thought so. And they came up with what's called the hydrogen bomb. And this is interesting in terms of the nuclear physics. This is really horrible in terms of what it does, of course. It makes use of both fission and fusion, okay, things we've talked about. What they realized was, as we saw before from that nuclear binding energy curve, you get more energy out per unit mass from fusion than you do from fission. But as we also learned, it's very hard to make fusion happen because you're trying to bring charged particles together. So you need very high temperatures and very high densities to make that work. Well, what better way to do it than have a fission bomb go off? Okay? Because that makes very high densities and very high temperatures. And so this is a cartoon. What it doesn't say, what you can't see up there is this was a design by Teller and Ulam, the US people who figured out how to do this. And there was a similar group involving folks in Russia who did it. So what you have is what's called a primary. Okay, that's the fission weapon. And in this one, it's an implosion type device. And what you do is you set that off to generate high temperatures, high pressures, and oh, by the way, neutrons and X-rays, which then cause this device, which is the fusion part of it, to implode and have fusion happen. Okay, and then it turns out from the fusion, you also make more neutrons and you make more fissions. So it's actually a three-stage kind of device: fission, fusion, fission. And these are drawings of the sequence of events that happen. So you start out with the weapon before firing. You have a high explosive to trigger the fission part of it, the primary. In this case, it's compressing plutonium, making fission reactions happen. Then you get X-rays and neutrons. The X-rays are used to heat up the area around the fusion device and make it implode and also heat it up. You also get neutrons rattling around. And inside the core there, you've got some more plutonium to make some extra neutrons. And in this area inside here, the gray, you have a fusion fuel, which is lithium-6 deuteride. And what happens there is the neutrons from the fission interact with the lithium. You get lithium-6 plus a fast neutron, and it makes, so let's do this right. So here's 3 and 3, 0 and 1. So I get tritium, which is the thing I want. And what have I got left over? I've got 2 helium. So I make tritium just when I want it to be there. because then the tritium can fuse with the deuterium, which is there, and because they're at high temperatures, we actually get a decent fusion reaction happen. We generate 14 MeV neutrons in that process, and those neutrons then run into U-238, which is surrounding it all, and because they're 14 MeV, now you can cause that to fission too. So fission, fusion, fission, and you get an enormous amount of energy. I think the Russians exploded one device like this that had a yield of 50 million tons of TNT equivalent. It was the largest one ever done. Lithium-6 is stable. Right. So these, in terms of radioactive decay, I think have no particular shelf life. Again, they worry about the aging of the components because the components are just sitting there. Everything deteriorates with time, and they're getting exposed to a fair bit of radiation from the radioactive material, which is there, the uranium and plutonium. Yeah. I saw that too. I actually don't know. I don't know what the tritium, you're talking about this thing up here. Pardon? Yeah. Say again?
Could the tritium boosters used to make the fission device more powerful?
Uh-huh.
Then you actually get more compression out of it. So just like if you compressing it to orange like this, you get compression. But if you clap your hands against the orange, you get more compression.
So you have more mass coming in, more inertia. Right. So how do you, sorry, what did the tritium do? I missed that.
It's a boosting for the fission primary.
Right.
So,
what's it doing?
For this kind of weapon, they use it for
Somehow you're making neutrons?
you get fusion out of that tritium.
Oh, so it's TT fusion.
You get TT fusion.
Okay, that was my guess. I wasn't sure. Okay. Very good. I didn't know that. I didn't know that. Very good. Okay, I learned something too. Right. Other questions? So, a little bit of nuclear physics, a little bit of nuclear forensics. So one of the things these people who would analyze the debris would do is, as I said, go out and collect samples and measure the radioactive decays to try to figure out what happened. And you've seen this kind of curve before, which is an indication of the way particular nuclei fission in terms of the production of the fission products. So each one of these curves represents the distribution of fission products you get from a particular compound nuclear system fissioning. So this curve labeled U-236 really means neutrons plus U-235 making fission. And the one labeled Pu-240 is really plutonium-239 plus a neutron undergoing fission. And you can see that over on the right-hand side, the curves more or less lie on top of each other. That is, for the heavier fragments, the distributions are very similar. But on the lighter side of that dip, there's, in fact, a fairly large difference, especially on the very light side. And so people discover that you can distinguish what the fissionable material is on the basis of the distribution of the fission products that were produced. And this is part of what's called nuclear forensics today. And this sort of shows you one little characteristic of it, which has to do with the fact, again, as we've talked about before, that in the fission process you make very neutron-rich nuclei, primarily. They then beta decay, and over time the distribution or the number of each species changes. So this is a plot for mass 89 that got produced by the fission of U-235. It turns out that 4.4% of all fissions of U-235 produce a mass 89 nucleus, but it doesn't get produced all in one isotope. And so at t equals 0, right after the fission happens, the black squares represent the abundance of each particular isotope. And so initially what you make is primarily bromine 89, but over time it decays, and if you wait 1,000 seconds, now you've got mainly rubidium 89. And so depending on at what time you do your measurement after the fission event, you'll see a different distribution. So you need to know when the thing happened to interpret your results and to know what to look for. So we did some experiments, and lots of people have done experiments like this to sort of see how much you can learn in terms of the fission products and identifying what the source was. And since we've been to the cyclotron, I thought I'd tell you a little bit about it. The cyclotron doesn't produce neutrons directly. It produces beams of charged particles. So what we did is we took a deuterium beam from the cyclotron at something like 16 MeV or so, and we ran it into a beryllium target. And you know that deuterons are very weakly bound. It doesn't take much to break them apart. And so the collision of the deuterium beam with the target is sufficient a lot of the time to break the deuteron apart. You get a free neutron and a proton. The proton stops in the beryllium target. The neutron just keeps on going. And then what we did to the effects of thermal neutron-induced fission is we built a big polyethylene moderator that surrounded the target, let the neutrons wander around in the polyethylene and get thermalized. And then we had a system that's called a rabbit. It's a pneumatic system for transferring samples in and out of this area very quickly. And so we could shuttle a target from a location outside in here, irradiate it for some short period of time, and then shuttle it back out to where we were, away from this nasty radiation, and where we had germanium gamma ray detectors that could then measure the gamma rays that were emitted following the beta decays of the material. And we did this for U-235, plutonium, all kinds of different things. And if we wanted to study conditions more like what would happen in a nuclear weapon, we would get rid of the moderator and use the fast neutrons that got produced directly from the beryllium target and allow them to hit the target and then cause the fissions. And just to show you some of the data, these are curves, these are germanium gamma ray spectra taken following the irradiation. The red curve is for fission of U-235, and the blue curve is for fission of plutonium-239. And the only point to get out of this is there are lots of individual lines, which we can work backwards and figure out which isotopes produce them. But notice there's some fairly large lines here, 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 and here, which show up quite prominently when it's U-235, which is fissioning, and they're much weaker or totally absent when it's plutonium fissioning. And if you go back to those fission yield curves I showed you, it's exactly what you'd expect. So this is the kind of nuclear forensics people would do in the event of a horrible accident or terrorist nuclear weapon going off. They'll use this to figure out details about what the bomb was, what it was made of, hopefully to help figure out who did it and to figure out what to do next. And you can use this not just to figure out which isotope it was. There's lots of information contained in these spectra, a lot of which is classified. But you can also figure out the energy of the neutron that caused the fission to happen. So if you were trying to figure out, was this a hydrogen bomb type device or was it a crude nuclear fission device, by looking at these kind of spectra, you can actually figure that out. Because again, there's a different distribution of fission products produced by 14 MeV neutrons versus low energy neutrons. And this is just trying to show you that as a function of time, things change. These spectra are taken at different times, and you see the spectra evolving. So again, you can use that information to figure out what's going on. Okay. I mentioned that we and other countries did lots of tests. This is a histogram showing worldwide nuclear testing. Again, doesn't show. It's from 1945 to 1998. We're the blue. The Russians are the red. And various other countries are the other colors. This was nuts, I mean, in my opinion. We were doing thousands and thousands of tests. And over the years, we realized we didn't need to do this, so we signed various treaties with the Russians to stop doing first above-ground tests, because a lot of the tests were done initially above ground, as you saw, both in Nevada, and then, we blew up the Bikini Atoll in the Pacific to see what happened. Really, really insane. We learned better, so we quit doing nuclear testing. We signed an agreement where basically we and the Russians and several other countries have agreed we will no longer test any nuclear weapons at all. And that provides a whole host of problems given the fact that we have thousands of these things sitting around, and there are people who want to make sure that in the event we need them to work, they still will work. So it's a very interesting problem. How do you guarantee that these things will work when you're never allowed to turn it on? Okay. And a guy I met at Livermore gave me a very nice analogy once. He said, the problem of trying to make sure these weapons work is like the following. So there's a guy who wants to get married. And the father of his bride-to-be says, look, I'm going to give you a brand new Cadillac, very fancy car, that is to be used only on the day my daughter is going to give birth to her first child. Okay? You can never turn it on between now and then, but it absolutely positively have to work that day, because if she's late to get to the hospital, I'm going to kill you. Okay? So how does this guy make sure that car, which he can't ever turn on, is going to work on that day way off in the future? That's the problem the people who want to maintain the weapons have. It's a very difficult problem, and it's a serious problem because we decided we still need these things for various reasons, and so you want to make sure they would work if, God forbid, you had to use them. And how do you tell that they will? So there are people at places like Lawrence Livermore, Los Alamos, and other places around the world and other countries trying to do the same thing. In our country, we call it stockpile stewardship, okay, trying to maintain the nuclear stockpile so that if, God forbid, you had to use it, it would. And this shows you the numbers. So this is a histogram of the total numbers of nuclear weapons that both we and Russia, now formerly Soviet Union, had. You can see, we had ridiculous numbers. They've estimated that if you wanted to destroy both countries, you need a few hundred weapons. Okay, we had 50,000. It's just nuts. So we've, through various treaties, gotten down to the point where we have something like 10 or 15,000. The Russians still have more. There is a treaty now being negotiated, basically right as we speak, to try to reduce these numbers by another 20 or 30%. Hopefully that'll happen, and hopefully, we can bring these down further. President Obama talks about getting rid of all nuclear weapons. I'm not sure you can actually do that. I'm not sure you actually want to do it either, but that's a whole other discussion. So these are bad things. There are lots of them out there. A lot of interesting physics, and they do terrible, terrible things. Okay, I'm happy to answer any more questions. If not, we'll stop here, and then we'll have a review on Friday. Yeah. They don't tell me. A lot of them are basically out in the field, ready to be used. So there are nuclear weapons on submarines that are, swimming all over the oceans. They're on airplanes. And then a lot of them, of course, are in storage at secure locations all around the country.